we were discussing expectations on different spaces, right. I partially proved this theorem. Right. So, we have omega x and y equals g of x. So, this theorem is saying that you can either compute. So, this is the expectation of y. So, you can either integrate on this space, right, that is that, or you can integrate on this space. So, basically you can compute integral g dp x with the probability law here, right. So, you can either go ahead and find the probability of law of y and integrate this, or you can just keep the probability law of x and integrate g, right. So, they are equal. So, this is something that you probably use without really, without really knowing why it is true, right. So, that is what we were trying to prove. So, we proved it for simple functions, right. Proved for simple functions last lecture. Simple G previous lecture. So, if G is a simple function, we proved that integral G dp x is equal to integral y dp, right. So, that was proved, and it was trivially equal to integral y dpy, because it was only taking those finite values y 1 through y n, and you could just write this as sum over y 1 probability y equal to y 1, right. So, in the simple, when G was simple, it is very easy. Now, if you have to generalize to non-negative G, then you have to approximate G from below using simple functions. Suppose G is non-negative and measurable. Let G n be a sequence of simple functions such that G n increases to G, let us say for all x. Okay. Can I always do that? Because I have that explicit construction, we can take that G n which we wrote down, right, by chopping down the vertical axis. So, you can always do that. So, now what happens is you will have, so G n's are simple, right. So, you will have G n of x, G n of capital X will be random variables, simple random variables, which monotonically increase to G of x, right. So, thus G of x, G n of x, let us say. So, G n is a sequence of simple functions. So, G n of x will be a sequence of simple random variables, right, and since G n increases to G, I can write G n of capital X increases to G of x, correct, fine. Now, what do we know? So, now I know that for simple functions my result is proven, right. So, I am going to exploit that. So, I want to write integral y dp, right. So, this is what I want, integral y dp, that is nothing but, so this function, so y is a, so you should look at this as a function mapping omega to this r, right, y is a, so that I can write this as integral g of big X dp. So, g of big X is the random variable, right. So, I am computing expectation of y, which is nothing but the expectation of g of capital X, correct. So, I have that, right, this is the LHS, right hand left hand side, this is equal to limit n tending to infinity integral gn of x dp. Why is that? MCT, monotone convergence theorem, that is because gn of x is a sequence of random variables that increases to g of x. So, this is because of MCT. Now, I know, so this guy I can deal with, right. So, this guy is equal to limit n tending to infinity integral g n d p x, correct. So, I am just looking at, so if you just focus on this part of the statement, right, I am saying that integral g t d p x, if g is simple, integral g d p x is equal to integral g of x. So, y is nothing but g of capital X, right. So, integral g of capital X dp is equal to integral g dp x, but that is true for simple functions, correct. So, I am just using that, this is equal to that because we have already proven, right. This is because g n is simple, we already proved that previous lecture, fine. So, that is the key step. Now what happens? Do I know this limit, this what, this is equal to integral g dp x, again because of MCT, because gn is increasing. So, here I am using the fact that gn of x is a sequence of increasing random variables. Here I am using the fact that gn of little x, right, is a sequence of increasing functions, that is it, right. So, when I write g of capital X, I mean the random variable g of x of omega. When I just write little g n or little g, I mean the function of x, little x, correct. That is the notation I have been following, okay. So, this has been proven. So, I have proved what I need to prove for, so I have proven this for any non negative function g, right. Then the next step will be to write, if g is arbitrary, we will write g is equal to g plus g minus, then it will work out, all right. So, the proof is over then. So, this is just saying that if G is my identity map, right, G is my identity map, then integral y dp is same as integral little y dpy, right. So, I can either, so for any random variable x or y, let us say, expectation of y can be computed by integrating y dp or integral little y dpy. If you look at that, right. So, you can either integrate over the probability space or integrate over R, okay. So, you can that is a trivial corollary, right, for any random variable x, integral x dp is equal to integral little x dpx, okay. That is a simple corollary of this, okay. So, by now you would have realized that practically, I mean, all basic results in integration are proved in exactly the same way. You start off with simple functions and then you generalize to non negative functions. Now, there are two ways of doing it. You either use the supremum definition or now you use monotone convergence theorem. There are two options, right. So, one of the two is what you keep using. Good. So, this proves the theorem. Next, I want to move on to expectation of continuous random variables. Expectation of discrete random variable we already covered, right. Now, I am going to derive an explicit formula for the expectation of a continuous random variable. So, what the main result, the main formula is going to use integration over different spaces and in conjunction with Radon-Nikodym theorem. Okay. So, let us this is something I should have done earlier probably. So, Radon-Nikodym theorem I sort of stated imprecisely because you did not really understand what an abstract integral was back then, right. So, now let me just recall Radon-Nikodym theorem and state it properly. Okay. So, recall Radon-Nikodym theorem. So, P x is absolutely continuous with respect to lambda, the Lebesgue measure, if and only if there exists a measurable function f x from R to 0 infinity such that for all Borel sets B, P x of B is equal to integral f x d lambda over B. Okay, so, this is an if and only if statement. Right. So, I am stating this properly now for the case of absolutely continuous measures P x with respect to Lebesgue measure. Okay. It holds more generally for any two sigma finite measures. Okay. I mean in fairly general spaces, but this is the only thing of concern to us. So, P x of, so it says that there exists a Radon-Nikodym derivative f x or the density f x such that for every Borel set B, P x of B is equal to integral over that Borel set f x d lambda. So, this is exactly what I wrote down, except now you completely understand what this means. I am integrating f x, which is a measurable function, non negative measurable function with respect to Lebesgue measure on a Borel set. Okay. So, now you understand this completely, right. And then we went on to say that, oh, if the Borel set is minus infinity x, then my CDF is equal to integral minus infinity to x f x dx, right. So, from now on it does not really matter if you write f x dx or f x d lambda, because as I mentioned, if the Riemann integral exists, the Lebesgue integral will always exist and the two values will be equal, right. So, even if I write integral f x dx, you can just interpret it as a Lebesgue integral. It is safer to interpret it as a Lebesgue integral because it is more general. So, I am going to use this theorem on different spaces, this expectation on different spaces in conjunction with Radon-Nikodym theorem to derive an expression for the expectation of a continuous random variable. So, let me say this as a theorem. Let x be a continuous random variable on omega f p and let p a measurable function which is either non negative or satisfies integral absolute G G is a measurable function from R to R, isn't it? So, absolute G G d px is less than infinity. Then expectation of g of x. So, expectation of g of x is equal to integral g so integral g f x d lambda. In particular, expectation of x is equal to integral x f x d lambda. Okay. So, this is the theorem. So, this is what you have been using, right, for a continuous random variable x. If I ask you to find the expectation of x, actually in elementary courses you define this as the expectation, right. If x is a continuous random variable, you say the expectation is integral x f x dx, correct, and for a discrete random variable you define it as sum over a I p of a I, right. So, expectation was defined very disparately for continuous random variables and discrete random variables in more elementary courses, and if the random variable is a mixture or something, you will have to invent another formula, and now we know that actually there are singular random variables mixtures thereof, right, and for those none of your elementary formula will work, right. But so, what we have, so the mathematically sound way of defining it is to just give one uniform definition integral x dp and particularize it for discrete continuous whatever you have. Okay. So, the definition is the same, expectation of x is integral x dp, right, integrate the random variable with respect to measure p, that is the definition, and that gives you different formulae. Okay. So, the discrete formula that you are familiar with comes out of that, and so does the formula for continuous random variables. Okay. So, in some sense, so this is not a definition, this is something we are going to prove, right. We define the expectation as integral x dp and prove that this is the formula for expectation of x for a continuous random variable. So, this works for actually, so there are some technical conditions. So, this definitely works for non negative functions g, okay, in which case the integral is always well defined, and it also works when the g is absolutely integrable, meaning that g plus and g minus, if you write down g plus and g minus, you do not have the infinity minus infinity kind of problems. Okay. You have a very well defined real number, right. In both these cases this works. So, any questions on the statement? So, integral x f x, so this is x f capital X d lambda, f x is the density, right. So, we expect on f p, so with PDF f x. Okay. X is a continuous random variable, so it has a density, and the expectation is given by the integral of x f x d lambda. Okay. This is over the whole real line. When I do not say anything, it is over the whole real line, right. In more elementary notation, you will write this as integral minus infinity to infinity x f x of x dx, right, except now I am writing it as a Lebesgue integral, that is all, right. You already know this formula, this is nothing new. How would you prove it? Assume G is simple, right. So, every theorem in integration you can start off by this statement, right. I think you can never go wrong by starting off with simple functions. Assume G is simple with G of omega is equal to sum over ai I of omega I equals 1 through n. Then expectation of g of x. See, now I am going to use the expectations over different spaces, the previous theorem. So, I am going to write this as integral g dpx. Okay, this was the equality you proved in the earlier theorem, okay, and actually g is simple. So, this certainly holds, and now this is equal to. So, you are integrating a simple function, g is now simple with this form with respect to some measure p x. So, this should be equal to what? By definition, right, this is equal to sum I equals 1 through n a I p x of. So, I am integrating with respect to measure p x. So, p x of a I, is not it, big A I. But p x of a I already know. What is p x of a I? Radon-Nikodym theorem, right. So, integral over a I f x d lambda. Okay. So, let me do that. A I integral over big A I f x d lambda. So, this is because of Radon-Nikodym. So, this is because of integration over different spaces, this is because G is simple, and that is because of Radon-Nikodym. Okay. Now, you can see there is a scaling law for integrals, right. So, I can bring the a I inside here, fine, and I can then I will have a summation integral, correct, that is equal to. So, sum over I equals 1 through n integral capital A I f x d lambda. This is because of the scaling property of integral, right. You can always bring constants inside and outside. So, I am going to write this. So, now what is the integral of a function over a measurable set defined as? In terms of the indicator, right. So, I can write this in terms of the, let me do this properly, sum over I equals 1 through n integral. I am not going to write a I now, I am simply going to write a I. So, little a I indicator a I and f x d lambda, that is by definition of the integral over a measurable set. So, now I have a summation and an integration, right. So, this is a finite summation, correct. So, this is a finite summation. So, sum of a finite number of integrals is equal to integral of the sum, again by the linearity of integrals, right. So, integral g plus h is always integral g plus integral h, you have n such terms here, right. So, the by linearity, so that is equal to sum over I equals 1 through n. So, okay, integral, I put the integral out, a I I a I can bring the f x out and then put a d lambda, correct. Now, what is that? What is inside the parenthesis here? G, correct. So, that is equal to integral g f x d lambda. So, the proof is complete for g simple, okay, good. So, now, I will have to approximate for any non negative g, I will have to approximate g using simple functions from below, right. Now, next let g be non negative. Non negative and measurable. Let g n be a sequence of simple functions such that g n increases to g. I know I can always do that, right. I can always write any non negative function as a monotone limit of simple functions. So, that is always allowed. So, now I have to write. So, again I have to try and do this, right. So, now I have to use monotone convergence theorem, right. So, I will write expectation of g of x is equal to limit right. You will agree with that because of MCT. This is equal to, so expectation of g n of x we have already sorted out. G n is simple, right, we already know what that is. So, this is equal to limit n tending to infinity, I am just keeping the limit, and then I can write integral g n f x d lambda, correct. Now, what can you say about this integrand? So, the integrand converges to g f x certainly, right. Does it converge monotonically? Why? Because f x is non negative, f x is a non negative function. So, this guy increases to g f x. So, this is a monotonic convergence, right, because f x is non negative. So, again monotone convergence theorem will help you, right. So, you can take the limit inside. So, again by MCT, you have integral g f x d lambda. Okay. So, you can see how powerful MCT is, right. So, combined with the fact that there is always some sequence of simple functions that you can approximate from below, right. You can prove properties very explicitly for simple functions and use monotone convergence theorem. It is very powerful, it is a very powerful result, and it gives you for all measurable, positive measurable, non negative measurable functions. Next, of course, if g is possibly negative, you have to write it as g plus and g minus, g plus minus g minus, and in that case this will help you that the fact that this integral is the absolute integral is bounded means that the positive part and the negative part are finite, and so you will not have any problems of blowing up and so on, right. So, then this everything will go through is the same. Okay. Okay, so that is the formula to remember, right. So, this is what you would normally write as. So, in more elementary courses you would write expectation of g of x is equal to integral minus infinity infinity g of little x f x of little x dx, right. This is what you have been using, right. That is exactly what we have proved, except this looks a little different, but it is the same thing. I have written it as a Lebesgue integral, that is all. Okay. And in particular, if you are computing expectation of x, you will simply integrate x times the density over the whole space. Okay. Now, you can take all your favorite continuous random variables, right. We listed exponential, Gaussian, one sided Cauchy, two sided Cauchy, right, integrate happily and find out their means, right. So, if you have an exponential PDF mu e power minus mu x, you can prove that the mean is 1 over mu. Okay. And for the n mu sigma square, the Gaussian, mu will turn out to be the mean. Okay. So, you have an exponential random variable, and if you want to compute expectation of x is equal to integral x f x d lambda, which is equal to nothing but x mu e power minus mu x from 0 to infinity, right. This will turn out to be 1 over mu. Okay. If I give you some other function, let us say x power n or something, you can still compute it, right, because we know that integral, you will just integrate x power n f x d lambda if you want expectation of x power n, right. So, for example, if you take expectation of x squared, you will simply integrate x squared f x d lambda, right, which is x squared mu e power minus mu x dx, and this will be equal to 2 over mu square, if I remember correctly. Okay. You can calculate it, right. These are integrals you can do by integrating by parts or there are standard integrals basically. Okay. So on. If you have a Gaussian, your expectation of x all this, right, e power minus x minus mu squared over 2 sigma squared over sigma root 2 pi dx. So, in order to do this integral, you can make a substitution x minus mu over sigma equal to t. Okay. If you make that substitution, you will get a you can do it much more easily, all right. So, in this basically this will simplify to just mu. Okay. So, in order to do you can put, so in order to do this integral you can put x minus mu over sigma equal to t. Okay. Then you can do this integral easily. If you have, to give you another example, if you have f x of x is equal to 2 over pi 1 over 1 plus x squared, x is greater than or equal to 0. So, this is a one sided Cauchy distribution, right. In this case, expectation of x be equal to integral 0 over infinity 2 over pi x over 1 plus x squared dx, right. Now, if you put 1 plus, if you put x squared equal to t, 2x dx would be dt, right. So, this will become log, so it will become 1 over pi log 1 plus x squared, I think, evaluated from 0 to infinity, right, and this will be equal to infinity plus infinity. Okay. So, the one sided Cauchy has a infinite mean. Okay. What if you take a two sided Cauchy? If I have f x of x is equal to 1 over pi 1 over 1 plus x squared over all real numbers x, then you will have the the x plus component will have an infinite mean, the x minus component will have an infinite mean. So, the expectation is, so is it 0 or not defined? Not defined. When you have infinity minus infinity form, it is not defined. Okay. So, let me just write down, if you have f x of x is equal to 1 over pi 1 plus x squared for all x in R, then expectation of x is undefined. So, the two sided Cauchy, or what is normally represented what is normally talked about as the Cauchy PDF, Cauchy distribution, expectation of x is undefined, it does not have a mean, right, it does not have an expected value, whereas the one sided Cauchy has a well defined expected value of plus infinity. Okay. So, this is pi times 1 plus x squared for all x both. So, it is both over positive and negative x. So, here expectation of x is undefined. Okay. Okay. So, when you are given a random variable which takes both positive and negative values, ideally you should integrate. So, you split it as x plus and x minus, evaluate them separately. So, here I have generally taken the liberty of integrating from minus infinity to infinity ideally. So, this is this Gaussian takes both positive and negative values. So, you split it as positive and negative and make sure they are both finite in this case. So, I could take the liberty of integrating from minus infinity to infinity. In this case you cannot integrate from minus infinity to infinity. In fact, so if you try and do that, you will get some function like this, right. You will get, if you just blindly apply the formula x f x, you will get an integral like that, right, 1 over. So, you will get x over pi 1 plus x squared dx, right. If you blindly apply the formula, this is what you will get. And this integral, well, this integral does not really, see, the problem is this integral does not, it is not really 0, the integral is not 0. Okay. The reason this integral is not 0 is because, remember, when you even in Riemann integral, when you define integral minus infinity to infinity, you define it as limit m1 tending to infinity, m2 tending to infinity, minus m1 to m2, correct, and that limit does not exist, right. So, even if you were to, so this is by definition limit m1 to infinity, m2 to infinity, integral minus m1 to m2 all that dx, right, and this limit does not exist, it does not exist, right. In particular, it is not defined as limit m tending to infinity minus m to m all that is not what it is. So, if it were defined as limit m tending to infinity minus m to m of this odd function, then you will say integral minus m to m of an odd function is 0 and then the limit is, it is not true, right. So, that limit m tending to infinity minus m to m is called the Cauchy principal value, it is not the value of the integral, right. You might have studied this in calculus, right. So, this is the, this integral does not exist, it is not 0, okay, it is undefined, this is undefined, right, this limit does not exist and it is not 0 in particular. But in this case there is no such problem, okay.
Except from Cauchy, in all the random variables, the mean is inside the range of the random variable. It is between, it is finite, but in the Cauchy it is infinite, even though the random variable don't take the value infinite.
Yes, correct. So, what this says is that a random, see, after all a Cauchy random variable or even the random variable, the discrete random variable, right, 6 over pi squared, 1 over k squared, we looked at that. So, those are, see, obviously these random variables are finite with probability 1, right, they have to take only real values with probability 1, but the expectation can be plus infinity, right, that is what it means. So, there are random variables whose expectation is in fact plus infinity, but they are finite, they never take the value infinity, right, they are finite with probability 1, they only take values in the positive real number, they never take the value plus infinity, but the expectation can be plus infinity, no problem, okay. Are there any questions? So, is this very clear? Okay, so we have dominated convergence theorem remaining, dominated convergence theorem and Fatou's lemma. So, it is probably too little time to start it now. Okay, so we will I will stop the lecture here.